Here we're going to integrate trigonometric functions. Before we do any examples, there's some formulas that one should memorize. The integral of the cosine of x is the sine of x plus a constant as usual. The integral of the sine function is -1 times the cosine function plus the usual constant. And the integral of tangent is -1 times the natural log of the cosecant of x plus the usual constant. These are not functions we'll derive here, but things we'll just memorize for use in our examples. Let's take a look at this integral here. So it's important to remember when you're integrating with trigonometric functions, you use the same techniques, rules, and strategies that you would use for any integrals that weren't trigonometric functions. So it might be a good idea here to employ substitution, letting u, a new variable, be the argument of the trigonometric function. Watch and sort of remind yourself how integration by substitution would work when you were doing this lesson in your past. You may recall you would take the differential of both sides, leading to this, and then you would isolate dx so that you could go back to the original integral and replace dx with an expression that involves the differential du. Here I can factor out the 1 over 3 pi, and I simply have this integral reduced to the integral of sine. But remember, the integral of sine is -1 times the cosine, so I can replace that here. You might wonder why I use the letter k instead of c. Well, it doesn't really matter. Just picked a letter. There's kind of had a reason you'll see in a minute. But either which way, now that we've taken the antiderivative and have a function of u, remember to unsubstitute or to replace back what u represented. U was a placeholder for 3 pi x plus 1, so I can now replace u with 3 pi x plus 1. This would be a certainly fine and acceptable answer, but for no particular reason other than neatness, I decided to distribute the 1 over 3 pi. When we multiply 1 over 3 pi times the constant k, we get some other constant, which I can call any other letter I want, and I've chosen c here for no particular reason other than it's traditional to end with a plus c. Here we'll take a look at our last example. This is going to be a definite integral. You'll notice we have numbers for our limits of integration here. Again, we're integrating a trigonometric function, but all the same strategies that we learned when we weren't doing trig functions and integrals are still applicable here, of course. It may be a good idea to remind ourselves what sine cubed means. It means that the sine function is being cubed. And therefore, I think it would be a good choice to let u represent the inside of that cubic function. U equals the sine x. Probably is going to be a productive substitution here. Watch and you'll see. As usual in substitution, once we've chosen our new variable, we differentiate both sides and get a differential equation. And then we isolate dx so that we can go back to the problem and replace dx with our newfound expression. You'll notice I also replace sine x with u. Now here, the nice thing is the cosines cancel. And really, that's just a testament to the fact that my choice of u was a clever one. Now, I was careful here to write the x equals in the limits of integration to remind ourselves that while the integrand and the differential are functions of u, the limits of integration are still functions of x. No matter, we're going to change back to x anyways. So we'll take this expression here, and we'll integrate it like we normally would in very basic calculus, 1/4 u to the 4th. But before I plug in my x values, I should unsubstitute or replace u with what it originally stood for. Remember, u was chosen to be a placeholder for sine x, so I can plug that back in. And now, just like we would for any other integral, we plug in the upper and lower limits of integration and subtract. There's absolutely nothing new about this whatsoever. What does feel a little bit new here, though, is that we have to evaluate the sine of 2 pi over 3 and the sine of pi over 4. That's not particularly difficult for some people if you did well in trigonometry and you understand the unit circle. It turns out that the sine of 2 pi over 3 is radical 3 over 2, and likewise, by the same fashion, the sine of pi over 4 is radical 2 over 2. If this seems mysterious or that like it was learned many, many years ago and it's way out of your reach, you're going to want to go back to the lesson where you found this video, and you'll find a lesson on the unit circle that will explain where those fractions came from. Putting that aside for the purposes now, we simply have to work out what these are. You'll notice I'm raising two things to the fourth power. I did that work on scratch paper and it's not shown here, but just to remind you, something you learned in 7th grade, if you're going to raise something to the fourth power, multiply that number by itself 4 times. The results are shown, the work is not. It shouldn't be too hard for you to figure it out. Doing a little elementary school fraction work gets me to my final answer.